Okay, were you able to download it? Please, anybody that confirm me? Anybody confirming me that you received this? Anybody?
Yeah, we received.
Okay, if somebody did it, we're fine. Okay, so let's take this case. You see that it's an undetermined beam problem because we have three reactions, two on the left, one on the right. We cannot simply apply a static equilibrium in order to solve for the reactions. We have to do the fourth order and all of that. And you see that this is it's not complex, it's just long, very long, because we have to integrate from 0 to L/2 and then get the displacement and rotations, then integrate from there to the right, and then set in the connecting point, we have to set continuity, displacement, and rotations. It's a very long process. Okay. And also shear force and displacement because it's continuous. Finite elements, let's see what happens. Okay, discretization, that's the first step. Of course, in this case, we are working with beams, so we think that we can model this as beams. How many? 2 is enough, right? So we see that on the left, the sectional inertia is twice on the right, so we have to recognize that difference in the model. That's that. This is the equilibrium equations for the first element. And you see here that this is what it means. Means that this is the element 1. Okay? But here, this is, I don't put it this thing here because I'm talking about the one single, one common way of numbering all the joints. Okay, this is not the first and the second joint, it's just of this element. It's just the first and the second joint of the whole system. Okay, again, for the second one, here is the number of the element, and you see that this is equal to that. This is equal to that, because I just wanted to save one step. And we know that because of continuity, they have to be the same in order to avoid breaking the system. Okay? So in this case, we recognize immediately that this is different than this. And we're fine. We're fine. This is something that we know. This is what we call consistency. So here, I have one external force that we don't know. But here, the external force that we need here has to be splitted to have both beams in equilibrium. And this is what we say here. The total external force has to be splitted. Part of that will be employed for the equilibrium of the first element and the rest for the equilibrium of the second element. But as a total, we have to have F2y. How much F2y? How much is this? How much is this one? Mr. Zambrano, how much is F2y? Big F2y. How much is this? Mr. Arias, are you there? Mr. Arias?
Yes, doctor.
How much is this?
I can see where you put the mouse. Okay,
what?
I am sorry.
F2y. How much is F2y now?
I think.
How much is the external force applied in joint 2? How much are we applying here? Mr. Galarza, how much force are we applying here?
Zero.
Exactly. That means that this part here has to be equal to that one, but with opposite sign. Because we have to be consistent. There is no external force there. See, all of that has to be represented in this simple equation, algebraic equations. Now, in this way, we can put the two matrices for each element together. And that's what we call the global matrix. So that's the first force, okay? So it's just equal to F1y of the first element. That's easy. That's a bit more complex. So this is what we call F2y of the first element. This is F2y of the second element. Because the two elements have this joint in common. And we recognize immediately that this displacement is equal to this displacement. So this value here will be added to this value here when we put one single equation. Okay, that's what we do. So this element here, because it's multiplied by 2, and this element here, and all of this is multiplied by d2y. This is the way they link all these elements together. Okay, after that, we go on and we have to consider, remember that we have only the first subsystem. Okay, in the first subsystem, we do not know the displacements. Now, in this case, I'm showing you how to form the global stiffness matrix. Okay, so this is the first. This is like your where am I? Here am I. So this is like your K of the first element. This is your K. For the second element. And then what we do is we combine it. Okay, this is just this in a more compact way. Okay, we see immediately that this is the first element, this is the second element, and this is the linking. And the link is performed in the second joint. So this corresponds to the second joint. Okay, so this is a global matrix. In this case, it's a 6 by 6. We have 3 joints and we have 2 degrees of freedom per joint. The solution. Remember, we have to have enough geometric boundary conditions or points of support in order to avoid rigid body motions. So in this case, we recognize from our previous courses that no translation, no rotation because it's clamped. And here, no translation. That's what we're saying here. This is no translation, no rotation because it's clamped. And here is no translation because it's simply supported. That's that. This is the stiffness matrix, okay? And remember that this is really what we know as a big number and multiplied by d1y. This is the value that we need in order to have this equation to recuperate this value. In this case, this value is 0. That's why we put it 0. Similar for this one. Similar for this one. If you have a value different than 0, then you have to set up this expression and put it into here. And you see here that this number is very large compared to this one. So when you put these terms together, okay, mathematically means that this is so large that you can neglect all of them. So it's like saying you're multiplying this times d1y and it's equal to 0 because all the other terms are so small. And the solution, of course, has to be d1y equal to 0, which is the condition. But the advantage of this is that otherwise, you will have to take this part here, these two, and these elements, and form a new matrix. And that takes a lot of time. Instead of that, you do this. That's the solution. Okay. We can try to show the I can't find the pointer now. Anyway, you can see that the deflection will be like this, then go downwards, and they have to go up like this. Okay, so we see that the deflection here, because of the moment, has to be negative downwards. This is what we see here, negative, and rotation is going to be negative. And on this, on the other end, the slope is going to be positive. So this makes sense with that. Okay, right now, as we can see here, right now, all of this is known. See, it's completely known. We found the values that we did not know, and the others were conditions. So what we have to do is multiply this vector, displacement vector, times the global matrix. And that's what we obtain. I'm sorry, this is again the displacement, and this is the force. So this is the force and the moment on the clamped end. This is something that we recognize. There are no total external forces in this joint, no at all. And this is the reaction here. And this is the applied moment. This is the applied moment that it was data. I took it a value of 1 to simplify things. Okay, so because of this moment, this action like this, we should have to have a reaction like this, okay, in order to overcome in this direction. But if we have a force here, we need another force here to cancel this one. And this is what we are seeing here. Okay, so we have a pair like this, we pair a pair like that, and we need another one here in order to equilibrate. And that's what we have here. Questions, people? Questions? Questions? No? Okay. Now, we have solved displacement for the global, in this case, coincides, but for everybody. We could go on to analyze each element. For example, in this case, this is the deflection of each element. Okay? So remember, these are the polynomials that we worked with this morning, multiplied by the joint, displacements, and rotation for every element. Okay? Remember, this part here, this is common. The only difference is the length of the element. The rest is these polynomials of order 3. These are the polynomials. We know exactly everything is here is known. And right now, these 4 values we have calculated for every element. And we can go on and plot. Okay? So here, what we need to do is we identify this is for the joint 1. This is joint 1. This is joint 2. And this is joint 3. And in yellow, see, I'm circling. These are the 2 joints which define element 1. And in blue are the 2 joints which define element 2. So what we need to do is take these 4 values in yellow, put it into here, and we can approximate the displacements in this part here, which corresponds to the first element. Then we can take these 4 values, put it into here, and approximate the displacement in the second element. This is what we have here. Okay, so from here to here, this is element 1. From here to here, this is element 2. And you see that this point here, this value, Jesus Christ, this is D2Y, which is common for both. And this rotation, this is phi to Y, to Z, which is also common. Here, displacement and rotation is 0. Here, displacement is 0, and rotation is positive, is this value. That's the analysis for each element. In this case, the solution is exact again, because we have no distributed load inside the elements. So the solution in this case, it's cubic and it's exact. We have to analyze stresses. We need internal forces. That's the internal force for every element. That's the bending moment for every element. So this is constant. This is linearly varying. Okay? In this case, since we have no, remember, dv and dx is equal to what? Anybody? dv at dx? Mr. Ortega, dv dx is equal to what?
Minus pi, minus p.
Minus p. And how much is p in this case? In this case,
0.
How much is p? Is 0. That means that v is a constant, and that's what we have here. Again, in this case, dm dx, I'm sorry, mc is ei v comma xx. So if this is cubic, the second derivative is linear, and that's what you see here. But this is obtained using, for the first element and for the second element. Exact because remember that we are approximating, but we are taking the same polynomial or type of polynomial, cubic, to approximate, and that corresponds to the exact solution.
Doctor,
Yep.
I have a question.
Go on.
What will happen if for example, the joint 2, we will have a punctual force, or in the bar number 1, we have a distributed force. We only adapt the P of X to the force?
No, just a second. 2 questions. What happens if I have a force here?
Yeah, it's a concentrated force, for example.
Yeah, in that case, well, we need to go back here. And in that case, what would you change here? That's this force.
The F, yeah.
Yeah, for example, you put +3. Exactly there. Or if you have a moment here, then you will change this value here. Because remember, these are external forces applied on the joints. If you put it downwards, then you will have to change the sign and put it minus the value. Okay, that was the first question. The second one, that's the more complex. Okay, let me write it up here. Okay, you have to be patient because we're going to do this in the next chapter. Okay, let's suppose we have something like this. Okay, so we have to convert this into this. Because here, we cannot apply anything because we're only worried about the equilibrium of this and that. We're going to do that. And what we're going to do is calculate statically equivalent external forces. And we're going to use an energy approach. Basically, it's something like this. It's the integration of P of X times the vector of the ends and dx. Don't worry, we're going to deduce in detail, but that's what we're going to do. So here we have 4 elements, right? The integration multiplied by this will produce the external force, equivalent external force. The second will produce the moment. The third, this, and the last, the moment. So we're going to convert this into something like this. Patient, we're going to get into that next chapter. I don't remember who did this question.
Carrion.
Okay, carry on. Okay. Did I answer your concern?
Yes, yes,
Okay.
yes. Thank you so much.
No problem. Anybody else, people? Anybody else? So in this case, we can start thinking that there's going to be some error, right? And what we need to do is, if we have doubt, what we can do is we can put another joint in between. See, I always like to maybe you have been in Guayaquil. Have you been in el Parque Forestal? You see this dome like this, right? You are a couple of blocks away, and you see a curve, right? But you can get closer. That's not a curve. It's composed by little triangles, which are flat. So it's basically, you are doing something like this. From here, let me try to change color. Okay, I don't want to use yellow just in case anybody gets, but that's what you do here. Okay, and then you go from here to here. Jesus Christ. And then, okay, now, let's suppose that you don't like it. What you can do is include another joint here. And you see that you go like this, like this, like this. So even though you are approximating this curve with straight lines, since they're very short, you can follow the curvature very closely. That's the idea. Okay, so if you have a P of X integrated, will give you, I don't know, maybe a fourth order, fifth order polynomial. That's for the exact solution. Using little cubics, you can approximate the exact solution. If you have doubts, what you have to do is include one more joint and compare. If you see that the differences are small, you are fine. If the differences are large, that means that you're still away from the convergence. You have to go again. That's something that you did in the numerical analysis. Okay, people, for this, is there no more question? This Wednesday, we're going to have the evaluation. Remember, at what time is the evaluation? Mr. Sanchez, are you there? Mr. Sanchez, are you there?
Yes, doctor.
At what time is the evaluation on Wednesday?
10 a.m.
Yes, 10 a.m. At 12, we're going to have something to share. I'm going to invite you. There are other friends or your classmates who are going to share also with you. If you can bring anything to share, that will be fun because it's really a very nice occasion so we can share. And that has to be from 12 to 1 because at 1, we have to go to the lab in order to go on with the, there is an experiment in mechanical vibrations class. Okay, so we can have this break. If you want to come earlier, that's fine. I'll try to set up the coffee machine so there will be coffee all the time. Anything else? I will provide, of course, the papers. You have to bring calculators and something to write, of course. Anything else, people? Anything else? There is a question from Nevares.
At 7 a.m.
Armin?
We still have class at 7 a.m.
At 7 a.m.?
Wednesday. Sorry.
That's, yeah. Yeah, on Wednesday we have the quiz at 10. And at 1 p.m. we have the experiment for the finite mechanical vibrations people. Some of you are in both classes, so we have just 1 hour break in order to go to the other activity. Please, I just want to transmit you the warning that we received from our dean, from Alejandro. Everybody has to cooperate. Please, everybody has to cooperate. Okay, so let's try to avoid being too close. Let's try to use all the time our masks. Okay. Bathrooms, restrooms will be open, so you can share. You can wash your hands as often as you want. Please, if you can bring your own alcohol reservoir, so you can either use or share with other people. So let's try to think that the problem is here yet. So everybody has to cooperate. Remember, stay away at least 2 meters. everybody has to use masks. Okay, if somebody is talking, it's not eating, it's not, but it's talking without mask, somebody should call his attention. Please wear your mask. If you are getting too close, would you please? These are simple things, right? But everybody has to cooperate. Okay, is there anything else, people? Otherwise, that will be all for today. Remember, for this evaluation, I have two homeworks. That's chapter 1. And from the second chapter, we wanted to include the review on beam bending, just the first part. This is just a review from your solid mechanics class. No questions? Then I'll see you Wednesday. Bye-bye now.
Thank you, Doctor.